Hello, my name is Stanley Franzik. I'm a member of the Sheehan STEM team, and this is our presentation on Module 4. Our mission was to conduct a critical design review as well as develop a prototype of our final design to make sure that it meets requirements by doing qualification testing. We also provide a status update on our risks, bill of materials, and project schedule.
Hello, my name is Billy Syme, and I will be presenting the final prototype of our final design. This is the 3D model we created in Module 3 of our design. We then created more parts to incorporate it into our prototype for this module. The design remained the same with a single drum and motor that drops down to a movable pulley and connects to a fixed point underneath the Arduino. The parts we created in this module were the motor casing, which will hold the motor and the drum, as well as a motor cover which will go over the motor casing, as well as a base for the motor casing with an opening for the line to drop down to the movable pulley and connect to the bottom of the Arduino case, which has a loop that will serve as our fixed point, as well as hold the Arduino above the loop.
My name is Gretchen Sipes, and I'll be talking about our requirements and qualification testing. So the requirements we were given are what our design should be able to do. The first requirement we were given was that our hoist had to hold a 3-pound load with a factor of safety of 1.5. This load should also be able to be lifted up to the bottom of our design. And while we are lifting this load, it should be able to limit vibration, shock, and rotation. It should also be able to have a cutaway system, so if it is being overloaded, it can cut away the line to prevent any damage to our design. We should also have a control system so we can communicate with our design effectively. So the qualification testing goes hand in hand with the requirements, since we use the qualification testing to make sure that our design can fit the requirements. So the first test we will conduct is a static limit load test, which will be using a calibrated weight set in our design. We will use this to make sure our design can actually lift the 3-pound load and retract all the way up to the bottom of our design. We will also conduct a reliability test to make sure that our cutaway line can effectively cut the line every single time. We will do this by putting our servo through a certain number of cycles and make sure that every time it can do it, so we can qualify that it is reliable. For the rotation test, we will drop the load down and lift it up and count the number of rotations. We want to do this to make sure that our design doesn't have really high number of rotations or sometimes really low. We want to have a very consistent number to make sure there are no flaws within our design. The vertical shock test and lift speed test can go hand in hand. We will use the vertical shock test, we'll utilize an accelerometer, which will measure the amount of G's applied to the load. The lift speed test will measure how long it takes for our design to drop and lift the load. We want to do these together because part of our challenge is being able to lift the load, lift loads in a certain amount of time, but also we don't want to apply too many G's to our load. So we want to do them together so we can calculate the speed that doesn't have too many G's.
I'll be presenting a status update. So for our project plan, we basically relatively stayed on track for what we wanted to complete for this module, and we started a little later than we would like to on our research and our filming process, but we stayed pretty much on track for this module. For our risk, in the last module we discussed the mitigation for the third risk, which was the rope disengaging from the pulley, and as mitigation we created a barrier to go around the movable pulley to serve as a connection for the line, as well as a connection to the hoist pendant. And we are currently in the process of 3D modeling this barrier and 3D printing it, as well as the servo, which we will connect to the challenge rig to cut the line when it gets snagged in an obstacle or outside forces. And that will serve as a mitigation for our fourth risk, as well as complete a requirement for the entire challenge as a whole. For our bill of materials and project budget, it remained mostly the same, besides with the addition of the 3D printing filament, which was used to print the parts for the prototype. As well as we changed our pricing because we realized that in a realistic consumer arena, the customer will be buying these products and it comes as a cost. So previously in the last module we had Vex Gear, all these were zero because they were as no cost to us because we already had the parts at our school, but we then realized that they would have to be bought by someone in a realistic area, and so then we added the cost to our final project budget as well as the cost of the 3D printing filament, which leaves us with $72 remaining for our final budget for the remainder of the project.
We would like to thank you for listening to our presentation of Module 4.